So yeah, hello. I think I was already introduced by the session chair, so thanks for the introduction. And yeah, I want directly to start with the first slide and the question, why do we want to investigate radius order models or ROMs regarding non-residential buildings and zoning strategies? So the first reason is that non-residential buildings are accountable for around 11% of global energy-related CO2 emissions, as we can see here. Regarding simulation, non-residential buildings come with higher effort for creation and parameterization of the simulation model compared to residential buildings. And they also come with higher computational effort to solve the resulting system. And another thing is that the necessity of zoning the simulation model, which is not a must-have in regarding residential buildings, for non-residential buildings can't be neglected anymore, and the heterogeneity of non-residential leads to the need of this. Another fact is that radius order models often neglect the interzonal heat transfer, and this point, combined with the necessity of zoning the building, brings us some additional problems I want to talk that we want to investigate. So, and the last point is that the existing investigations for radius order models are focused on single room buildings or small buildings on the one side, or on the other side, urban scale building or on urban scale. And therefore, we want to investigate this, the usage of radius order models for single, bigger non-residential buildings. So, in which cases is the radius order? So this brings us to two main questions we want to discuss in here. The one is, in which cases is the radius order model approach suitable for simulating larger non-residential buildings? And the other question is, how do different zone strategies or zoning strategies for radius order models affect the accuracy and the computational effort? And also, how's the effect of this neglected interzonal heat transfer? So how do we want to answer these questions? For the first one, we modeled the same building with two approaches. One approach is the VDE 6007 based multi-zone radius order model in Modelica that can be created with teaser. And the other model is the EnergyPlus model, which is a much more detailed model. And to create comparable models, we are using a BIM model as a single source of truth. I will talk about this later in detail. So, and the second question regarding the zoning strategies, therefore we are applying different level of zoning merging to the teaser model. These merging methods later on are based, or these merging methods are based on previous research, rules of thumb and guidelines. And after we carry out the different simulations, we want to compare them regarding accuracy and computational effort. I'll give a rough overview about the use case. It's the KIT Institute building, which is where we have a BIM model in the IFC, which we use. It's a high quality BIM model with second level space boundaries, and it's created in ArchiCAD, and it has not the most complex geometry, but anyway, it's not trivial geometry. And we have rooms of different type of usage. We have single and group offices. We have meeting rooms, transport areas, bathrooms, and an attic. And the big question is now how we want to create comparable models in different simulation environments. Therefore, we are using our self-developed BIM to Sim tool chain, which creates us an IDF and a Modelica model. Both models are resistance and capacity-based models, whereas the Modelica model, the radius order model, uses a much more simplified approach with just, and we are using the two-capacity approach, where we have just one capacity for all external walls and one for the inner walls per zone. Both models adopt adiabatic inner walls. And both models go with the approach of every room is a zone. So we have 82 rooms in here. So this leads us to 82 zones. The material data is that we use is carried out by the teaser templates. And this is directly implemented into the BIM to SIM toolchain, which allows us to use the same material data for both simulation models. The toolchain is also capable to use directly this information in the BIM model, but the BIM model doesn't come with completed material data, so we use this way, and therefore use a template with for construction year of 2015 and light construction type. And for the weather conditions, we're using a test reference year for Aachen in 2012. So now we have our comparable models. Now it's the question, how do we want to compare them? First, we had to look at the ASHRAE 140, which delivers specifications on how to compare simulation environments. But the problem is that this only gives us test cases covering really small one-room buildings. And therefore, we created our own test scenarios, which are loosely based on the ASHRAE 140 test cases. But anyway, provide us the possibility to compare the two models. So, which are these scenarios? We are investigating two characteristic days. The first is the 20th of January and the second is the 27th of July. We are defining two characteristic rooms for the that we want to investigate closer. One is north and one is south oriented, as you can see on the picture below. And both have a glazing ratio between 60 and 7% and are similar size. The KPIs that we want to compare are the annual heating and cooling demand, the free floating temperatures for both rooms on both days, solar irradiation for both rooms at both days, and the heating and cooling power at these days, these rooms. So let's start with the annual performance. We carried out the following simulations, and as we can see, the reduced order model has a slightly higher heating demand, while it has a slightly lower cooling demand on an annual base. And also the peaks, as we can see here, the peaks are higher for the heat. The peaks in heating demand are higher for the reduced order model and lower for the cooling demand. And in general, we can see that it's the heating demand is 10% higher, while the cooling demand is 10% lower. We also see that the reduced order model, as I said, tends to higher heating peaks and lower cooling peaks. But in overall, we can say that the qualitative and quantitative behavior between the two models is quite similar, even as one is a reduced order approach and the other one is a detailed approach. When we are taking into account that the EnergyPlus model, when looking at existing research, as in general, is at the lower boundaries of the allowed heating demand in the ASHRAE test cases, this makes also sense that the reduced order model has a slightly higher heating demand. So far with the annual performance. Now let's have a look at the detailed performance, and there we can see. The first look goes through the free floating temperature, and there we can see that we have quite unrealistic high temperatures, and both for the south orientated room here, the north orientated room here. So both the reduced order model in colors, as well as the EnergyPlus model in dashed lines, has really high temperatures. Even in the north orientated room, we have, or even in the winter times in the south orientated room, we have between 30 or 35 or 40 or 45 in the EnergyPlus model degrees Celsius in the rooms. And this is due to the over-discretization combined with the assumption of adiabatic inner walls. As I said, this model has 82 rooms or 82 zones. So every room is a zone, and we don't allow it to exchange heat to other rooms. So this leads into these high temperatures. What we can also see is that the reduced order model calculates lower temperatures in both cases, and the difference here is higher for the south orientated room. So first we assumed that this might come from the solar radiation because it's different for the two models. So we had a closer look there, and we found that the solar radiation is quite similar. Anyway, we have a slight delay between the reduced order model and the EnergyPlus model. But we can assume that the solar irradiation is not the reason for the lower temperatures, because in general it's quite similar. So far regarding the comparison of EnergyPlus and the reduced order model. So now we come to the second question, and there we first need to answer how to merge the zones. So as I said, the reference is this 82 zone model. The rooms were merged by combinations of these following 4 criteria: parameter core, where we divide into internal and external zones; orientation, where we divide into northeast and southwest; glazing ratio, where we divide into these 4 categories; and usage, where we just divide every usage type as its own category. So all the relevant information to carry out this deviation of rooms, or this merging of rooms, can be extracted from the BIM model. And this results in 5 setups to further investigate. And the questions here that we want to answer, or the 2 sub-questions, are: the first one, how to reduce the computational effort? And the second one, can zoning be used to reduce the impact of adopting deviatic interior walls and zones? So can this help us to overcome this issue of non-interzonal heat transfer? So first question. Now these are only teaser models, so we compare them with each other. And we start with the reference case. We can see that the computation time is around 44 minutes for this 82 zone model, and its deviation is of course 0. But then we can create our first model with all 4 categories taken into account, and then we come up with a 12 zone model, which only uses 5 minutes then, so a large decrease in the simulation time, without really much decrease or deviation in the simulation results on a yearly basis. Then we can carry out the others. We can see if we only take the 3 categories, we get 9 zones and similar results anyway. If you're using only the usage to divide the zones, we are coming up with 6 zones, and now we are starting to have a slight deviation, and we are for cooling also a bigger one. And if you're using only the parameter core and orientation, so we come up with 3 zones, the deviation gets bigger, and the most deviation we get for the 2-zone approach, where we have around 35% deviation in cooling. So what we can conclude here? We can conclude that the computational effort can be reduced by 90% by reducing with the 4 categories approach. We have no loss in the accuracy on a yearly basis, as we can see here again. And we can also see that on the dynamic behavior is also quite the same. So this brings us with the estimation for those buildings that reducing by a 4-category approach, we can dramatically reduce this simulation time without losing accuracy. So then the second question, can zoning be used to reduce the impact of adopting interior walls and zones? And therefore we carried out an additional simulation with EnergyPlus. And by using not anymore the inner walls. So EnergyPlus is now capable of exchanging heat through the different zones. And this gives us a result where we have a reduction in 7.5% in heating and 22% in cooling. And if we look at the other approaches, we can see that the 6-zone approach here has quite similar results, or is even the same range. So what we can conclude is that by selecting suitable zoning strategies, the effects of adiabatic inner walls can be reduced for reduced order models. But we also need to conclude that, or need to state out that further research needs to evaluate general correlations, because this is now just an investigation for one building, and we need to carry this out for more. So in the end, we can conclude that regarding the first question, the reduced order model delivers quantitative and qualitative comparable results to the EnergyPlus model with deviations of plus minus 10% on the annual basis. The reduced model tended to have lower temperatures and higher heating and lower cooling loads. And we found that for detailed analysis on single room basis or short period, we should consider detailed models and not the reduced order model. Regarding the second question, we divided it into sub-questions, computational effort. There we found an immense reduction of computational effort for the Modelica-based multi-zone model without a loss in accuracy when using the four-category approach. And regarding the second question of assumption of adiabatic inner walls, we found that using the use condition-based merging, we can reduce the unintentional effect of too high heating and too low cooling demands by this way. But this effect might depend on a large extent on the investigated building types, so there is further investigation for different building types needed. So this is everything from my side. Thank you for listening, and I'm looking forward to the Q&A.